In the previous video, we defined transformations in the plane. So for example, for A, we defined the transformation T of uv equals u plus v over 2 and u minus v over 2. And that took this square region in the plane and transformed it into a region that has a diamond shape. And then in example B, we looked at a change to polar coordinates that took a rectangular region, we'll call it S, and then that transformed it into a circular region in the xy plane, and that was T of S. Now, I would like to determine whether these transformations have an inverse. Is there a transformation, T inverse, that would take, say, the diamond-shaped region and turn it back into the square region, or take the circular region and then turn it back into the rectangular region? So in order to determine whether there is an inverse, we have to first ask the question about whether these transformations are one-to-one. A transformation T is one-to-one if T of u1 v1 equals T of u2 v2 implies that u1 and u2 must be equal and v1 and v2 must be equal. So this is similar to the definition that you would get in one dimension that said that a function is one-to-one if T of, say, u equals T of v implies that u equals v. The idea here is that if you have 2 points that are equal in the image, then they must have come from a unique point in the domain. Well, if we have a one-to-one transformation, we can then solve for u and v in terms of x and y. So we can think of u as being a function of x and y, and v as being a function of x and y. And then they form the inverse transformation, T inverse, which takes a region in the plane defined in terms of xy coordinates, and it puts it back in terms of the uv coordinates. So I would like to find the inverse of the 2 transformations that we looked at in the previous video. The first is that T of uv equals u plus v over 2 and u minus v over 2. And so those were x and y. In particular, x was u plus v over 2, and y was u minus v over 2. I'd like to be able to solve for u and v in terms of x and y. The way that I'm going to do this is similar to how I figured out what the image of the transformation is. I'm going to look at adding x and y. Notice that if I add x and y, the v's cancel. And so what I'm left with is u over 2 plus u over 2, which is just u. So u is actually equal to x plus y. Now if I take x and subtract y, then you'll notice that the u's again cancel. And so I get v over 2 minus a negative v over 2, and that is just v. And so now I've defined u and v in terms of x and y, and that is my inverse transformation. So it's T inverse applied to x and y is equal to x plus y, x minus y. And so this inverse transformation would take the diamond shape that you see there, all points that are within that diamond, and it would transform them back into that square region that you see there. let's look at the second example. The second example is t of r theta equals r cosine theta r sine theta. So in this case, x is equal to r cosine theta, and y is equal to r sine theta. And so what I would like to do is write r and theta in terms of x and y. And we know, in fact, that x squared plus y squared is equal to r squared. So in fact, r is equal to the square root of x squared plus y squared. We also know that y over x, as we've seen with polar coordinates before, is equal to the tangent of theta. And so we can rewrite theta as the arctangent of y over x. And in this way, we can define T inverse of x and y to be the square root of x squared plus y squared, representing r, and then theta is the arctangent of y over x. And we do need to be careful here when we define this inverse transformation, because that square root needs to be a positive square root, because we're only going to allow r to be positive. And then with the arctangent of y over x, we're going to have to pay attention to where x and y are in the xy plane so that we get the correct angle that corresponds to that particular quadrant where x and y lies. Normally, arctangent's only defined between minus pi over 2 and pi over 2. So we have to pay attention to where x and y are in the plane, which quadrant they're in, so that we make sure that we define that arctangent to correspond to the correct region in the plane. So these are just two examples of how you can create an inverse transformation. And that will be important as we move toward our goal of changing variables for double and triple integrals. The last thing that we need in preparation for this change of variables is something called the Jacobian. Now, the Jacobian is going to represent the derivative of these transformations in the plane. Okay, so in one dimension, the change of variables that we had was x equals g of u, and that resulted through the chain rule in that dx equals g prime of u du. Now we want to understand how is change of variables going to work when we have xy is equal to a transformation of u and v. So before, let's remember that we had the integral in terms of the variable u, and then we transformed the variable to x using the function g of u. The result was that the dx had to be rewritten as g prime of u du. Now I have that I'm going to change the variables u and v to x and y through the transformation t. And is there some notion where I can say, well, dx dy is the derivative t of uv times du dv? Is there such a notion for functions t which take a region in the plane to another region in the plane? Okay, and in fact there is. The notion is what's called the Jacobian. So the Jacobian of a continuously differentiable transform t, that just means that t has continuous partial derivatives. Okay, the Jacobian is a real valued function j, which takes uv and outputs something in the plane, R2, okay? And the Jacobian is represented by a matrix. That matrix has, the first row is dx du and dx dv. So that's actually the gradient of the x function, right? With respect to u and v. And then it takes the y function and also finds the gradient dy du and dy dv. So essentially, the Jacobian is a matrix that contains all the partials of x as a function of u and v, and then it contains all the partials of y as a function of u and v. So in fact, just like when we had a derivative, a notion of the derivative for a function f that takes a vector and returns a number, okay, the notion of the derivative was the gradient for those multivariable functions. Now, for these vector-valued functions, that take in a vector and return a vector, okay, the Jacobian is what now represents the derivative. Okay, so the Jacobian actually has many uses beyond just these change of variables that we're going to discuss in a moment. Okay, but we're going to focus our conversation about the Jacobian on change of variables. Okay, so now I want to get back to this question finally. Is there a notion that dx dy can be rewritten as, say, a derivative of my transformation, t, times du dv? So I'm going to present the change of variables theorem. The change of variables theorem says, suppose that the continuously differentiable transformation t, which takes a region in the uv plane and returns a region in the xy plane. Okay, so it's going to take a bounded region S. S is in the uv plane. And then the image of S is going to be a region I'm going to call R in the xy plane. Okay, so we have our transformation t. It's going to act on S in the uv plane. It's going to return another region R that's in the xy plane. We're going to assume that this transformation t is continuously differentiable, so it has continuous partial derivatives, and we're going to assume that it's one-to-one from the interior of our region S to the interior of our region R. That's so that we can have an inverse function t. Okay, well then, if my function f of xy is continuous on R, then we can rewrite the double integral in R of f of xy as a double integral over S of f of, and we're going to change the x coordinates to u and v coordinates. So we're going to do x of u and v, y of u and v. And then dx dy, we're going to rewrite as the determinant of the Jacobian. So these vertical bars mean the determinant of the Jacobian times du dv. So here what I mean is the determinant of the Jacobian matrix for that transformation, du dv. And so in fact, we have that dx dy is the derivative, the Jacobian times du dv. But in this instance, the derivative is going to be the determinant of that Jacobian matrix. Okay, so what we want to note is that here dx dy is the determinant of the Jacobian matrix in u and v du dv. So there's a couple things that I want you to note about this change of variables formula, okay? So the first is that it's a little bit in reverse from what we had in single variables. So you can recall in single variable that we looked at the integral, okay, of f of x dx as being a simplification of the integral of f of g of u, g prime of u du. So we actually started with this integral on the right, and then we simplified it to the integral on the left. But the general change of variables formula that we're going to look at, in fact, takes an integral that's written in terms of x and y, and then we're going to rewrite it in terms of something that seems like it's going to be a little bit more complicated. It's going to be an integral of f of x of u and v and y of u and v. And then we're going to multiply by the determinant of that Jacobian matrix, by that derivative, du dv. And so this change of variables is actually going to be in reverse of the substitution formula that we saw earlier.